Greetings. My name is Sai Amar Koduru from section CSCE, bearing the roll number 23211A05RA. Today I'll be presenting on the topic minimum cost spanning trees with inclusion of Prim's and Kruskal's methods and also their examples and algorithms. Okay, before moving on to the main topic, let's talk about a problem statement, which is a laying telephone wire. In this problem statement, what we have to do is we'll have to connect these given homes to the central office. The name approach would be to directly connect the homes to the central office individually, which is quite expensive because we are using quite a lot of resources and wires and the materials, which will also be clumsy. So the best or optimal approach is to connect each home in a way that the nearest home to the central office gets connected from, and the nearest home of that house would be connected. We are basically forming an optimized way to share and to connect the customers to the central office. Okay. The basic idea behind that is minimum cost spanning trees. Now let's talk about minimum cost spanning trees. Suppose you have a connected undirected graph with a weight or let's say cost associated with each edge. The cost of a spanning tree would be the sum of costs of its edges. A minimum cost spanning tree is a spanning tree that has the lowest cost, or let's say the least cost. Given below is the diagram uh, of a graph which is connected but undirect with weights. Okay, now minimum cost spanning tree for the given graph would be something like this, in which we are connecting the least cost values in such a way that all the vertices, or let's say the nodes, are connected to each other. As you can see, all the vertices are interlinked to each other in a way that the high or let's say the costly edges are not included. Now let's go in detail about the minimum spanning tree. MST. A minimum spanning tree is a subgraph of an undirected weighted graph G such that it is a tree. It covers all the vertices V, which means it also contains V minus 1 edges. So the number of edges in a minimum spanning tree would be number of vertices minus 1. The total cost associated with the tree edges is the minimum among all possible spanning trees. And a MST is not necessarily unique. Now, how can we generate a MST? Or minimum cost spanning tree. Given below is a diagram, or let's say a graph of it, in which, as we can see in the secondary figure, A to D. The cost is 2, which is the least among all the given weights. And from D, we'll go to C, which is 4, which is the second least value. And from D, we'll move on to E, exactly because it's again the second most least value. From E, we'll move on to B, because 9, 6, and 5. Yeah, this is the best way to move. So the graph, the MST would be something like A, D, C, DE, and EB. Now moving on to Prim's algorithm. It is similar to Dijkstra's algorithm for a connected graph. In Prim's algorithm, we will pick an arbitrary vertex S. We grow the MST as a cloud of vertices starting from S. We store with each vertex V a label D of V, which is the smallest weight of an edge connecting V to a vertex in the cloud. At each step, what we do is we update the labels and we will move on from one vertex to its adjacent lowest cost vertices. Okay, let's go delve into the deep of Prim's algorithm. T equals to A spanning tree containing a single node S. Now E, let's say it's a set of edges adjacent to S. While T does not contain all the nodes, we remove an edge suppose V comma W of lowest cost from E. If W is already in T, then discard edge V comma W. Else, we can move on from edge, add edge V comma W and node W to T. Add to E the edges adjacent to W. An edge of the lowest cost can be found with a priority queue. Testing for the cycle is automatic. Hence, the Prim's algorithm is far simpler to implement than Kruskal's algorithm, which we'll be discussing about later. And let's move on to another example where we are given a graph A. I mean, let's suppose an ordinary graph, and the starting vertex is A, and we are also given weights of the graph, so which would make it quite simple. Mm, From A, we will look for the edges and vertices and the weights. The least cost weight is A to B, which is 2, A to C, which is 8, and A to 7, I mean A to E, which is 7. Out of these, A to B is the least one, so we'll go from A to B, and later from B, we'll look for edges and vertices, A to D and A to C. As we can see, A to C is quite cost efficient. We'll move from A, B, and B to C. Again, from C, we'll look for its adjacent vertices. We won't backtrack over here. I mean, we won't return back. 8, 8, and 9. Since they are all costly compared to B and its adjacent vertex, which is D, so we'll come back and move from B to D. So after moving to D, we'll look for its adjacent vertices and which are least cost. D to C. We won't go back because I mean we won't go to C again because it would form a loop, and that's not what we are looking for. From D, so we have another possible only option which is F. So from D to F, and from later F to E, which is another least cost path. So in total, the MS team is A to B 2, 5, 7, 7 plus 7, 14, 14 plus 4, 18, 18 plus 3, 21. So our least cost path is 21. This is a brief example of, I mean, how we can solve it. Let's take the initial point as E. From E, we will move on to D as it's the least valued adjacent vertex compared to C and B. So from D, we will move on to A. And from A, we'll move on. I mean, no. From A, we will return to D because from A to C, it's 5 and A to B, it's 9. But compared to D to C, it's only 4. So we'll return back and traverse from D to C, which is 4. And again, we will go back to E and we'll go to B because E to B is least path. So the final minimum spanning tree is A, D, C, E, B. Okay, enough of Prim's algorithm. Now let's discuss about Kruskal's algorithm in detail. Let T be an empty spanning tree and E be the set of edges and N be the number of nodes in a graph. While T has fewer than N minus 1 edges, we remove an edge of lowest cost from E. If adding edge to T would create a cycle, then discard V comma W. Else add V comma W to T, which is edge values. Finding an edge of lowest cost can be done just by sorting the edges. Testing for the cycle. Efficient testing for the cycle requires additional algorithm, which is union find, which we won't be discussing currently. Kruskal's algorithm basically is we'll select the least value among the given set of weights, and from there we will connect the least weighted edges together, and at last we'll get an, let's say, what the primary goal is to connect all the vertices in such a way that the cost is the least possible one. It is similar to Prim's one in a way. Okay, let's go with the least value one. In the given example, I mean JFK to PVD is the most least cost valued edge, and later JFK to BWY, because 184 is the second least value, and later JFK to BOS as the given value is 187. Mhm. Let's identify another least value among the given weights. 337. Yeah. SF4 to LAX is the next least one. So we'll connect them. And now moving on to another least path, which would be ORD to BWI 621. JFK to ORD 740. And the next least path would be ORD to DFW and BWI to MI in the end. And the final connection would be from DFW to LAX. In this way, we have created a minimum MST by using Kruskal's algorithm and previously by using Prim's algorithm. That's it for my presentation. Thank you.